When it comes to gravity, the upper atmosphere, there is a zero action. At zero, there are lots of constant muons, and this muon can be used as a first source. So that's why we're interested in counting our property muon. The first is G-2 experience at Fermi-Max and achieve the most precise muon in the world, but require lots of resources. Our goal is to replicate the experiment but use a simple setup, make the measurement more successful. Also, one of the elemental parts of muon shares some property to the electron, like as spin and charge, but they are 200 times higher. Spin will catch the weight in the electron, and the KNS is defined as lifetime. Theoretically, the value is 2.2 microseconds. And there are both negative and positive muons which will decay into electron and positron respectively. The number of surviving muon is the exponential decay over time, and corresponding to a demo of number distribution, you can see when the lifetime is short, the number of muons is large, but it decreases significantly when lifetime becomes longer, which means that a few muons can survive so long. Another property for muon is G factor, and it's relative to a magnetic moment. Because of the magnetic moment, muon will precise in a magnetic field. Before introducing the precision, let's first talk about spin. Spin is the angular momentum of the angular particle and is intrinsic. Precision is the phenomenon when the spin direction starts to change. So you can see in this diagram that muon spin will start to change around the magnetic moment. In particle physics, there are two types which are like right-hand side and left-hand. And the difference between this where the spin and momentum direction are the same. Okay, let's go back to the magnetic moment. In this function, you can see there are three terms. In particular, interest in the first term, G factor. The theoretical value is 2, and we want to perform measurement. To do this, we'll use the precession frequency omega. So, because of the precession number, you will have a precise term. And looking at the right-hand side figure, you can see there is a small periodic oscillation within the exponential decay. So in a further analysis, we will find out the oscillation frequency to determine the G factor.
We have designed the setup to measure muon lifetime and G factor. We use a 15 times 15 centimeter scintillator to measure muon. When the muon hits it will generate the blue light. The PMT will absorb the light and change it to the electrical signal and amplify it. After that, we use the oscilloscope to collect the signal and record the data. The left-hand side picture is our setup. There's two scintillator modules. The top one is called channel 1. The other one is called channel 2. When the positive muon penetrates when the positive muon passes through all of them, it will be stopped by the copper block and decay to the positron. The positron will hit the channel 2. And the time interval is the muon lifetime we want to measure. For the measurement of the G factor, there's a coil surrounding the copper block. It can apply the magnetic field around 5 millitesla to make muon precise. To increase the event, we also place the lead plane to make muon slow down. We use two channels to select our event. When the muon passes through channel, it will produce the first peak for both. The time difference between it is within 1 nanosecond. Only channel 2 have a second peak from positron. This selection can help us to block down the fake event from another muon. We not only want to measure muon lifetime and G factor, we also make the setup to measure the muon incident point. Wavelength shift can absorb the blue light from scintillator and change it to a green light. The light will transmit along the fiber into an SIPM. SIPM can change the light into an electrical signal and amplify it just like PMT. There are 4 grooves on scintillator surface in X and Y direction. Each group has 2 fibers inside it. We also use another 2 scintillator to fix the block in the middle. Each scintillator block size is 5 times 9 centimeters. We combine 9 centimeter blocks into a 3 times 3 matrix. 3 blocks in column and row are share the same fiber. If the muon pass through 1, for example, if x1 and y1 are triggered, we can know that muon incident point is the top-left one. We only need to use 6 channels for 9 scintillators. This can cost down the readout budget.
Okay, so after we collecting data for several weeks, we calculate the lifetime from each event, and then we have the distribution of the lifetime shown here in this part. Theoretically, the relation between the lifetime and its entries should be exponential decay, but when we fill it with this exponential function, you can see the filling line and our data didn't match. So we believe there was some background being included. The background here means other charged particles like electrons or protons. So to find out the background, we remove the lead plate from the top, and then we collect the data from channel 1, which is the scintillator above. So after we found out the distribution of background showing here in this plot, we fill it with this filling function, 2 exponential term and an offset. With this fitting result is the model of our background. After we found out the background, we add its effect into our fitting function here. So you can see when we consider the background effect, the filling line and our data are better matched. And the lifetime we got was 1.66 microseconds, which is a little shorter than the theoretical value. The difference might be due to the sample size isn't large enough. In the case with magnetic field applied, we expect there should be small oscillation in our distribution. And you can see from here, at longer lifetime, a small oscillation appears. We find the precision frequency through fitting with its function and calculate the G factor of muon. The calculated result was 1.97, which is really close to the theory G mu equals 2. As for our muon tracker, the panel at the left-hand side are the channels of large analyzer. They correspond to each row and column in our data. So when cosmic muon hits a scintillator, the corresponding 2 channels will be triggered, and the LED light at the right-hand side will turn into yellow. So we can know which scintillator has been hit. These LED lights are actually the map of our scintillators. So with this experiment, we successfully demonstrated the potential of diverter as fiber, which can use for reduce the readout budget. Here, let's summarize our study. So muon is a particle will decay with a mean lifetime 2.2 microseconds, and due to its spin, it has a magnetic moment, which will lead to a precession in an external magnetic field. With knowing the precession frequency, we can calculate the G factor of muon. In our experiment 1, we used 2 scintillators for detecting cosmic muon, and then we stuffed them inside copper box with 5 milli-Tesla magnetic field applied. The lifetime we got was about 1.66 microseconds, and the calculated G factor was 1.97, which is really close to the theory. As for our experiment 2, we arranged our scintillators as a grid, and then we used large analyzer and LabVIEW control panel to monitor the incident points of cosmic muon in real time. That's all about our study. Thanks for your time.